Hello and welcome aboard here in my Calculus Conundrums. This section we're going to talk about applications of derivatives. So if you haven't seen my Conundrums over derivatives, you might want to watch those first. One of the first things that we talk about once we learn how to differentiate functions is we learn how to determine if a function is increasing or decreasing. Now I'm not going to give you the formal definition for increasing, decreasing, but I'll just show you the picture here. You'll notice here this function, as you go from left to right, you'll notice the y values are increasing. So this function is said to be an increasing function. Here, as you go left to right, the y values are getting smaller, so this is said to be a decreasing function. And then there's a constant function where the y values neither increase nor decrease as you go left to right. Now, it turns out that one function could actually be increasing for a period of time, and then it begins to decrease for a period of time, or vice versa. So that's what we're going to determine in the increasing-decreasing test. But before we can determine where a function is increasing and decreasing, we've got to define what is a critical number. A critical number is a number C such that either one of these two things are true. Either the derivative when evaluated at C is 0, or the derivative when evaluated at C is undefined. Now, the C must be in the domain, so that's important to remember. So if C is not in the domain, it cannot be a critical number. Okay, so let's take a look at some examples here. Make this a little smaller here so I can fit it on the screen. Okay, so in this function, at -1 and at +1, it turns out that the derivative is actually turns out that the function at this number has a derivative that equals 0. And I can tell that because if you look right there where it's turning around, what I'm drawing is the tangent line to the graph at the point -1, and I could also draw a tangent line to the graph at the point +1. And notice that the slope of these tangent lines is 0, so that would mean that the derivative of this graph at -1 would be 0, and the derivative of this graph at +1 would be 0. So therefore the critical numbers would be -1 and +1. Now, another way that you can get a critical number is if the function is undefined at a number. So take a look at this function. Notice at -2 the graph comes down and makes a sharp point, so like a corner. Well, and also at +2 it does the same thing. So there, when the graph makes a sharp corner or sharp turn like that, the derivative is undefined. So -2 and 2 are critical numbers because the derivative would be undefined at those values. Now also at 0, you can see right here that at 0 you would get a situation here where you would get a horizontal tangent line. So 0 is also a critical number because the derivative would equal 0 at x equals 0. Now, I'm going to show you another way that a derivative could be undefined, okay? And that's if you get a vertical tangent line. So this function here, at 2, the tangent line goes vertical. And remember, if your tangent line is vertical, it has no slope. Or we could say that the slope of the tangent line is undefined. So here, 2 would be a critical number because the derivative would be undefined at x equals 2. Okay, so how do we find these critical numbers? Well, basically what you do is you take the derivative of the function and set it equal to 0, and that will show you where the derivative equals 0. And then you also have to determine where the derivative is undefined. And that's usually only true when you have a denominator. Okay, now let me just go ahead and tell you this. If the derivative of the function is positive, which is greater than 0, for all x on some interval, then the function is increasing on that interval. If the derivative is negative, less than 0, for all x on an interval, then f is decreasing on an interval. And if the derivative is 0 for all x on an interval, then f would be constant on that interval. Now, I'm going to let you read these guidelines, so pause the video and read the guidelines here for the test for increasing to decreasing. But what I'm going to do is I'm going to just go ahead and show you several examples and how to determine the intervals where a particular function is increasing or decreasing. So don't worry, I'm going to walk you through this. So I'm going to do the test for increasing and decreasing for the function that you see here. And so you see that I have 2x cubed minus 9x squared. The first step is to find the derivative. And the derivative is 6x squared minus 18x. And notice I'm going to set that equal to 0. Well, you can factor 6x out and you get 6x times x minus 3. And then you determine when can that be 0. Well, it can be 0 when x is 0 or when x is 3. So the critical numbers are these numbers here, x equals 0 and x equals 3. Okay? Now, what we do is we create a table where we break the table at the critical numbers. So I'm going to draw a line right here. This is going to be where x is 0, and this vertical line represents where x is 3. Now what that does is that breaks up, let's pretend like this is the x-axis. Then that breaks the x-axis up into 3 intervals for this function's domain. It's everything less than 0, which is negative infinity to 0, everything between 0 and 3, which is 0 to 3, and then everything greater than 3, which is 3 to infinity. Now all I need to do is check any test number in each of these intervals and see if they make the derivative negative or positive. Okay, so now the reason that I don't need to worry about what's going on within these intervals is it turns out that since these are the only critical numbers, then there's no number in negative infinity to 0 where the sign of the derivative would change. And there's no number within 0 to 3 where the sign of the derivative would change, and so forth. So therefore, whatever any number that I choose in this interval, whatever sign it makes the derivative, then all the numbers in this interval will make the derivative of that sign. So I'm going to take -1 and I'm going to plug it back into the derivative. Now you can plug it back in here or you can plug it back into the factored form. Sometimes the factored form is easier because watch what happens when I plug it back into the factored form. Okay, so I know that 6 times x is negative, right? Because x is -1. And then I know that x minus 3 is negative because -1 minus 3 is negative. So I would have negative times a negative, which is a positive. So I know that when I evaluate the derivative at -1, I get a positive, and so that means that the function must be increasing on that interval. All right, let's pick a number between 0 and 3. How about 1? Okay, 1, if I plug 1 in, 6x would be positive, and 1 minus 3 would be negative, and positive times negative is negative. So I know that the derivative is negative at 1. So in this interval, the function would be decreasing. All right, and then here a number greater than 3 would be 4. So if I plug 4 in, I'll get 6 times 4 is positive and 4 minus 3 is positive. So positive times positive is positive. So therefore, I know that the function must be increasing in that interval. And so f is increasing on negative infinity to 0 plus the interval 3 to infinity, and it's decreasing on the interval from 0 to 3. And you can see the graph here. If you look at the graph, you can see here that as you go from negative infinity up to 0, it's increasing. Then when you go from 0 down to 3 here, it's decreasing. And then from 3 to infinity, it's increasing. Now looking at the graph is kind of cheating, so make sure you don't rely on the graph, because sometimes the critical numbers might be weird numbers and it might be hard to determine it from the graph. Okay, here's another one, and it's very similar to the first one, so I'll go through it rather quickly. So here I have x cubed minus 3 halves x squared. If you take the derivative, you'll get 3x squared minus 3x equals 0. And then if you factor that and set it equal to 0, you'll get critical numbers are 0 and 1. So here, when I break my number line up, I get 0 there, and I get 1 here. And so the interval here would be negative infinity to 0. Between 0 and 1 would be just the interval 0 to 1, and then to the right of 1 would be 1 to infinity. So pick a number in here like negative 1 and plug it into the derivative, and I'll get a negative times a negative again, which is positive. So the derivative is greater than 0 at negative 1, so therefore the function is increasing there. Pick a number between 0 and 1 like a half. 3 times a half is positive, and a half minus 1 is negative. So you have a positive times a negative, which is negative. So the derivative is negative on that interval, and therefore the function must be decreasing on the interval 0 to 1. And then pick a number greater than 1, like 2. And if you plug 2 in, you get a positive and a positive. When you multiply those, you'll get a positive. So the derivative is positive at 2. So therefore, the function is increasing. So the function is increasing on negative infinity to 0 plus 1 to infinity, and decreasing on 0 to 1. And here you can see the picture. It's increasing here, decreasing here, and then increasing here. Okay, I'll do one more on this video, and then I'll do some more examples on the next video. Okay, this one is x squared minus 4 to the 2/3 power. And if you apply the power rule to that, you'll get the derivative is 4x over 3 times x squared minus 4 to the 1/3 power. Now, it turns out that the derivative would be 0 if x is 0. So 0 is a critical number. But it also turns out that if x equals plus 2 or minus 2, the derivative is undefined. So critical numbers are also plus or minus 2. So you notice that if you put plus or minus 2 in the denominator, you'll get 0 in the denominator, and so the derivative would be undefined. So here I have negative 2, here I have 0, and here I have 2. Now again, I'm going to pick a number in each of these intervals that I got when I broke this up. And so in this interval, I chose negative 3. And if you plug negative 3 into the derivative, you'll get a negative number. I'll let you do that. But plug negative 3 into the derivative and see that you get a negative number. And so you know the function is decreasing. Now, from negative 2 to 0, plug negative 1 in, and you'll see that you get a positive number. So on that interval, the function is increasing. And then if you plug 1 in to this function, a number between 0 and 2 is 1, you get that the derivative is negative, so therefore the function is decreasing. And then when you plug 3 in, you get that the derivative is positive, so on this interval, the function is increasing. So the function is increasing on negative 2 to 0 and 2 to infinity. And you can see that here's negative 2 to 0, and there's 2 to infinity. And then the function is decreasing on negative infinity to negative 2, which would be this piece, and also decreasing on 0 to 2, which would be this piece right in here. Okay? So again, the graph should support our findings. So like I said, on the next video, I will actually do some more examples there. But one quick thing I want to tell you here is that when I chose negative 2 and 2 as my critical numbers, I had to make sure that they're in the domain of this function, and when I plugged them into this function, they were. So I didn't have a problem using negative 2 and 2 as critical numbers.